Hey guys, so for this problem here, we are going to use nodal analysis to solve for voltage A and voltage B. You can see here that if we know the voltage here and we know the voltage here, then it's pretty easy to figure out what the current is anywhere in this circuit. So let's get started. So the first thing I'm going to do whenever I'm doing a nodal analysis problem is I am just going to draw a current flow diagram. It doesn't need to be correct, but it does need to abide by Kirchhoff's current laws, which means I can't just have three currents all flowing into node A, and I can't have three currents all leaving node A. Basically, Kirchhoff's current law states that what goes in must come out. And so you can't have everything entering a node or everything leaving a node. So let's do this. So I'm going to say I think we've got a current going like this, and then we've got a current going like this, and another one going like this, one going like this, and one going like that. Now, if I'm wrong about any of these, I'll just get a negative value. Um, so here's our current flow diagram. So now I've got enough information to write some equations. So I need to write an equation for each of these nodes right here. So basically, I need to say for node A, say, I need to say this current minus this current minus this current equals 0. And for node B, I'm going to say this current minus this current minus this current equals 0. So let's do this node right here first. We're going to end up with two equations, two unknowns. So I'm going to describe each one of these currents. So we know that the difference in voltage across this resistor right here is this voltage minus that voltage. So that difference divided by that resistance is a current. So we're going to say, and we're going to also, let me mention, we're going to, whenever we describe these currents, we're going to go from the tail of the arrow to the head of the arrow. So we're going to start here and go there. So it's going to be 10 volts, that's the tail, minus VA divided by 100. That's that current. And then this current is leaving, so we're going to say minus VA over 220. VA over 220. And this current is leaving, so it's going to be minus. And I'm going to put a parenthesis around this just to remind me that I'm going to have to change the sign of what's in this parenthesis. So we got VA minus VB. And that is all over 330. And that equals 0. All right. Well, I need to put this equation into standard form before I can do much with it. So let's break it up into its respective pieces. So I'm going to break this into two pieces. So 10 over 100 minus VA over 100 minus VA over 220 minus VA over 330 plus VB over 330 equals 0. All right, so I notice this one right here, 10 divided by 100, which is 0.1, that is going to go over here. So I'm just going to say it minus 0.1, and I'll cross that out. Okay, so now I am going to factor out VA here. So there's this one, minus 1 over 220, that's this one, minus 1 over 330, it's this one, plus VB times 1 over 330 equals minus 0.1. All right, let me solve for the stuff in the parentheses. Not solve, but let me add up the stuff that's in the parentheses. So we got minus 1 over 100 plus minus 1 over 220 plus minus 1 over 330. So what is that? Minus 0.0175. So minus 0.0175 VA plus 1 divided by 330 is 0.003 VB, and that all equals minus 0.1. So there is our equation for VA in standard form right there. So let's do VB here. So that's this node. Well, this current right here is tail to head, so it's going to be VA minus VB over 330 minus VB over 470, and then minus, I'm going to be very careful about this, so I'm going to put parentheses around it, just to remind me that I'm going to have to change that sign, VB minus 2 over 25, and that all equals 0. Let's break this into its respective pieces. So we've got VA over 330 minus VB over 330 minus VB over 470 minus VB over 25 plus 2 over 25 equals 0. Let's factor out the VAs. So it looks like we've got 0.003, that's 1 over 330, VA, and then plus VB, and I'm going to have to figure these out. And then 1 over 470 minus 1 over 25. And what is 2/25? 2 divided by 25 is 0.08. So minus 0.08 goes over there. So let me figure out the sum of all these things in parentheses for just a moment. So minus 1 divided by 330 plus minus 1 divided by 470 plus minus 1 divided by 25 is minus 0.0451. So here is our equation. 0.003 VA minus 0.0451 VB equals minus 0.08. And that is our second equation in standard form right there. Now, as you guys know, there are many ways to solve systems of simultaneous equations. That is for another course. I am going to use the system solver on my calculator. So you can see I've got two choices here, a 2 by 2 or a 3 by 3. This is a 2 by 2, two equations, two unknowns. So we'll select 2 by 2. And let's enter in all these coefficients here. So we got minus 0.0175 VA, and then 0.003 VB, and then minus 0.1, and then we've got 0.003 minus 0.0451 451, and then minus 0.08. So here's what it's telling me. It's telling me that VA is equal to 6.08 volts, and VB is equal to 2.17 volts. Is that believable? I do believe it is. But we can check our work fairly easily here. So let's do it. Let's just see if all the currents entering and leaving node A here end up summing to 0. So we know that node A is 6.08 volts according to our solution. So what's the current here through the 100 ohm? Well, it's going to be 10 volts minus 6.08 volts. So there's 3.92 volts across this resistor. 3.92 volts divided by 100 ohms is 39.2 milliamps. So we got 39.2 milliamps going that way. Okay, let's see how much is leaving via the 220. So we've got 6.08 volts divided by 220 ohms. So that is 27.63 milliamps leaving this way. Let's see how much is exiting via the 330. So the difference in voltage across the 330 is 6.08 volts minus 2.17 volts. So there's 3.91 volts across the 330 ohm resistor. And so 3.91 divided by 330 is 11.84 milliamps. Okay. So if I'm correct here, then when I total 39.2 milliamps entering, minus 27.63 milliamps leaving, minus 11.84 milliamps leaving, I should get about 0. So let's see. So we got 39.2 milliamps entering, minus 27.63 milliamps leaving, minus 11.84 milliamps, and I get just a sliver, and that is just because I've been rounding. So I've got 270 microamps left over there, and that is solely due to rounding. So that means that I am correct here. If I wanted to get more accurate, I could add more significant digits here. You know, I could carry more digits in all these numbers right here, and I would get more accuracy. But for this particular problem, I don't think that's necessary. So I checked my work here. Basically, all of my currents here total 0. And if I do it here, all the currents entering and leaving this node are going to total to 0 as well. And that proves that this and this are correct. So that's it for this video, nodal analysis.